Time. Time creates a logical line of events. One thing happens before another one. However, only some things can precede others. For example, when we see a broken and an intact window, we tend to think that the window used to be in perfect condition and was later broken, since the opposite wouldn't make much sense. Similarly, if we see pure water and water mixed with ink, we will think that ink was introduced and mixed in with the water, but not the opposite, since mixed water won't spontaneously clean itself. This is a consequence of the second law of thermodynamics. It is important to note that there is a common misconception about that law. It doesn't exactly state that the universe tends to be more chaotic over time and loses its original perfection, since our universe doesn't think liquid water is less perfect than an ice cube. These definitions of chaos and perfection are arbitrary. Truth seems more complex, but it actually makes much more sense. Unfortunately, we don't have enough time to explain it thoroughly. However, we can at least say it's all about probability. Any isolated system is simply more likely to evolve into a state of higher entropy. What does it mean? When entropy is higher, the system, their particles, have more a variety inside. There are more possible configurations for those particles and their respective energies and other magnitudes. Since our universe loves variety, it is very unlikely the system will relinquish this new acquired diversity, and the more particles the considered system has, the less likely it is to lose that variety, and in our human scales that are very high in comparison to individual particles, we are always going to see an increase in entropy. So now let's leave this abstraction behind and think about the consequences. For example, if a tire is punctured, air will leave it since it is constantly gaining more entropy and won't go back to the tire because it won't accept losing this new variety or entropy. Similarly, sugar will mix in our coffee since it will gain more entropy in that process and won't go back to the spoon since it won't accept losing entropy either. This means the entire universe is in a state that won't last forever, since it will always want to gain more entropy. Everything that has ever been created will have to be destroyed. However, this obviously doesn't mean nothing can't ever be created in our universe. We exist, for example. Under the right circumstances, which we can call thresholds, complexity can arise and challenge the entropy. But the more complex it becomes, the more unstable it will be. So, how are we still here despite the relentless nature of entropy? To see how, let's be ambitious and take a look back at the entire history of the universe. 13.7 billion years ago there was nothing, not even time, but something happened and the universe was born, and it started to expand incredibly fast, even faster than light. This early universe was just an incredibly hot blob then. However, once the fundamental forces of nature started to come out, more complex particles were created. And all of this and much more paved the way for more complexity in the future. It took 370,000 years for the first atoms to be created. That's twice the time Homo sapiens has been on Earth. It took all that time just to get the first simple atoms in that opaque fog the universe used to be. We can still see hints of this fog when zooming enough. There's a microwave background covering the entire sky. In that background, we can see small variations on the fog temperature. These minuscule variations were caused by small quantum fluctuations when the universe was still very small, but later gave rise to the large-scale structure of the modern universe. How did it happen? Well, these random fluctuations made some places denser and others less dense. The regions with more density had more gravity, since there was more stuff there, and attracted more and more matter and would be the basis for future galaxies and groups of galaxies. In some places, the density became so high that temperature rose until reaching a new threshold, the creation of natural nuclear reactors, in other words, stars. These first stars could have formed 200 million years after the Big Bang and changed the universe forever. The nuclear reactions that take place in their cores form heavier elements like oxygen, calcium, and iron. At the end of their lives, these stars become supernovae and exploded, which, along with other stellar processes, created the other chemical elements, like gold, uranium, silver, and many others. Therefore, we should thank the stars for all the complexity we see in our daily lives. Even all of us are made of what dead stars created millions or even
So
billions of
now the
years ago.
universe is chemically more complex, and in a chemically more complex universe, it's possible to make more things. All the elements combine, they swirl around, the energy of the stars steers them around, they form the particles, they form snowflakes, they form little dust motes, they form rocks, asteroids, and eventually they form planets and moons. And that is how our solar system was formed 4.5 billion years ago. Rocky planets like our Earth are significantly more complex than stars because they contain a much greater diversity of materials. So we've crossed a fourth threshold of complexity. Now the going gets tougher. The next stage introduces entities that are significantly more fragile, significantly more vulnerable, but they are also much more creative and much more capable of generating further complexity. I am talking, of course, about living organisms. Living organisms are created by chemistry. We are a huge packages of chemicals, so chemistry is dominated by the electromagnetic force that operates over smaller scales and gravity, which explains why you and I are smaller than stars or planets. Now, what are the ideal conditions for chemistry? What are the Goldilocks conditions? Well, the first thing you need is energy, but not too much. In the center of the star, there is so much energy that any atoms can combine. We'll just get burst apart again, but not too little. In intergalactic space, there is so little energy that atoms can't combine. What you want is just the right amount and planets that are close to stars but not too close. You also need a great diversity of chemical elements and liquids such as water. Why? Well, in gases, atoms move past each other so fast that they can't hitch up. In solids, atoms stuck together, they can't move. In liquids, they can cruise, cuddle, and link up to from molecules. Now, where do you find such Goldilocks conditions? Well, planets are great, and our early Earth was almost perfect. It was just the right distance from its star to contain huge oceans of liquid water. Fantastic chemistry began to happen, and atoms combined in all sorts of exotic combinations. But of course, life is more than just exotic chemistry. How do you stabilize those huge molecules that seem to be viable? Well, it's here that life introduces an entirely new trick. You don't stabilize the individual, you stabilize the template. The thing that carries information, and you allow the template to copy itself. And DNA, of course, is the molecule that contains that information. You'll be familiar with the double helix of DNA. Each rung contains information. So, DNA contains information about how to make living organisms, and DNA also copies itself and scatters the templates through the ocean. So the information spreads. Notice that information has become part of our story. The real beauty of DNA, though, is in its imperfections, as it copies itself once in every billion runs. There tends to be an error, and what that means is that DNA is in effect learning. It's accumulating new ways of making living organisms because some of those errors work. So DNA is learning, and it's building greater diversity and complexity. We can see this happening over the last 4 billion years. For most of that time of life on Earth, living organisms have been relatively simple single cells, but they had great diversity and inside great complexity.